probably think there's no class because it's President's Day.
Yeah, if we don't have a class, we'll always talk about that the previous week.
Yeah.
Or I'll go through the pains to figure out how to communicate with you guys if I can't make a class. But typically I just keep going. If there is a holiday that's coming up that lands on a Monday that for some reason we don't want to do class, that's fine. If the majority of people want to skip a class because of a holiday or just because other stuff's come up, whatever it is, that's perfectly fine, we can do that. But unless it's explicitly stated, I'm always just going to count on doing class, which obviously everyone here expected. But,
Yeah.
all right, so let's remind ourselves of where we finished off last time. Where we finished off last time was talking about these axioms of arithmetic, or these fundamental axioms that we use in algebra. Now I told you that there's 3 other assumptions beside these that we really use, but these are the 10 that we're really going to focus on. And the majority of the way you can think about algebra is simply looking at what these 10 rules imply. These 10 rules pretty much imply all of algebra. And so all you're doing over and over again in all your algebra classes is applying these 10 rules over and over again, or rules we find out must be true, called theorems, that we get since we know that these rules are true. So the axioms are the foundational assumptions of our field. And these 10 axioms are our 10 most frequently used 10 assumptions, foundations of our field. So let's re-go over each of these and remind ourselves of what we're talking about. So for each pair of, we call them real numbers x, y. So this is saying for each pair x comma y in the real numbers, remember that weird looking R, that's going to be our symbol for the real numbers. Pretty much anything you think of as a number is a real number. For those of you who know what complex numbers are, then you obviously already know what the real numbers are. This isn't talking about complex numbers. If you don't know what I mean by complex number, what you think of as a number already is most likely just a real number. So for each pair of real numbers, there exists a symbol, we call that plus, a little cross symbol, we call that plus. So there exists a plus operation such that x plus y is always a real number. And there exists a little times operation. I told you I'm going to use a dot rather than an x, since x is often a variable we use. There exists a times operation as well, such that x times y is a real number. And these 2 operations, plus and times, satisfy these 10 rules. So we've got some mysterious set out there, R. We know nothing about R so far. It's some set of things called numbers. What's in there? Who knows? And we've got 2 operations, plus and times. What do we know about plus and times? I know if I grab 2 things out of this set and I plus them together, that gives me another thing in this set. And I know about times, if I take 2 things out of this set and times them together, that gives me another thing in this set. So far, that is all I know. And then the plus and times are also going to satisfy, the plus and times in that set are going to satisfy these 10 rules. You with me so far?
Yep.
So rule number 1. For any 2 real numbers x, y, x plus y is identical with the exact same thing as y plus x. Or in other words, addition is commutative. Commutative. X plus y is identical with y plus x. The order that you add them in does not matter. Addition is commutative. Rule number 2. For any 3 numbers, x, y, z, x plus y plus z is the same thing. It's identical with x plus y plus z. In other words, if I add y plus z, then I add x, that gives me the exact same real number as adding x and y and then adding z. Those both give me the same exact real number, therefore those 2 are identical. Good?
Mm-hmm.
Next one. Next one's our first information about our mystical set. There exists something in there, we're going to use this fancy symbol for it, 0. There exists that thing in there, whatever it is, and it has this special property. It has a special property that for anything else in there, when I add 0 to it, I get that same thing back out. So this symbol we call 0 has a special property that anything added to 0 gives me back that same thing. X added with 0 gives me back x. We call 0 the, anyone got the name for it?
Additive identity.
Additive identity. This is the addition operation. We call 0 the additive identity, because when you apply addition with 0, you get back identity, the thing you were adding with. When you take x, add 0, you get x.
So this is where I start to have problems, because 0 has some absolute value.
Zero,
the
so
difference between 1 and 0 is 1.
we have not proved that. You do not know that yet. All we know is that 0 is some fancy symbol that satisfies this rule. There's other things out there. For example, if I were talking about faults in logic, it operates so far the same way that I'm talking about this if I make that an OR operator. X or false is always equal to x. If x is true, that evaluates to true. If x is false, that evaluates to false. There's other things that have the properties so far that we've established 0 has. There's going to be other properties that make it the 0 we know and love from the real numbers. But for now, you have to let your intuition go for what you think about as real numbers. You have to stop thinking, I already know that the difference between 1 and 0 is equal to 1.
Yeah, so the whole absolute value proposition bothers me. I'm wondering if you're going to lecture on that.
I don't know what you mean by absolute value. Do you mean actually the absolute value function?
Yes.
We will define that function explicitly.
And I also mean that I don't like the property of 0 given that it has an actual placeholder. So like say the difference between positive 1 and negative 1 is what?
Well, we can prove that that's 2.
Exactly. So
but we'll prove those things from this property. It's the fact that 0 has this property and other things that lead to the fact that 1 minus negative 1 is equal to 2. This is a consequence of the properties of 0. You're reasoning backwards when you start thinking this way to try and logic about what 0 is.
Okay.
That's backwards. So these properties are what make the numbers that we know and love operate the way that they do. And it just has to do with these 10 properties. They give us all of that.
Okay.
So yeah, we'll define those things explicitly. But so far, so we know that whatever this R is, we now know that it has some symbol in there. We use 0 for it. We use a circle for it, and we call it 0. But it has some number in there, 0, such that anything added with 0 gives me back that thing. And so we call 0 the additive identity. It has an additive identity element, is another way it's frequently said. That's what Axiom 3 says. So now we know at least one thing in there. We know 0's in there. Axiom 4. Axiom 4 says for any number in there, there exists some other number in there, maybe the same number, maybe a different one, but for any number in there, there exists some other number in there, such that their sum is 0. So no matter what number I grab out of this set, no matter what thing I grab out of this set, I can grab another thing out of this set such that when I evaluate their sum, it gives me 0. That one make sense? Okay. So these four were telling us our properties basically of addition. You'll notice addition showed up in each of those. We're basically going to repeat these 4 properties again, this time with multiplication with a small tweak in there. So 1 and 5 almost say the exact same thing. For any 2 real numbers, the product now, instead of the sum, of x and y is identical with the product of y and x. Or in other words, multiplication is also commutative. These 2 basically say the same thing. For any 3 numbers, x times y times z is identical with x times y times z, which we call the associative property. So multiplication is associative. These 2. There exists some other mystical number out there. We call it 1, and we use that symbol for it. But there exists some element in there such that for any other element you grab out of there, when you take their product, x product with 1, x times 1, then that just gives you back x. We call 1 the multiplicative identity.
Okay, so do you tolerate questions about this?
Sure.
Okay. Because I don't like the incongruity of that. And the whole idea of multiplication is it's shorthand addition, right?
Whoa, no. Drop all those preconceived notions.
Okay.
What is multiplication? It is the symbol that satisfies these rules. It might be a freakish coincidence that multiplication is a faster way of doing addition. That might be some freak coincidence. But so far, what is multiplication? It is the magic thing that when you take two real numbers and multiply them together, it still gives you a real number, and it satisfies these rules. And that's all we know about it.
So they don't care about anything except these rules.
These rules make so that multiplication is a faster way of doing addition. And you can prove things like that. You can prove something like 5 times 5 is the same thing as 5 plus 5 plus 5 plus 5 plus 5.
Yeah,
And you can
until
prove
you
stuff
start
like
it, until you do that with 0, right?
Yeah, we'll have a special case that we prove for 0.
Is there
We
any
will
way to get
prove-
around these special cases?
We will prove, right here, it'll be the third thing we prove. Any number times 0 is equal to 0. That's a consequence of these up.
So you're gonna go through that?
I'm going to go through all the things we have listed
Okay.
here. Yep.
Awesome.
Okay. So, next one, let's see. Multiplication is associative, that's what this one says. Oh, we talked about identity element, so we now know a second thing in there. Okay. Third one, 8, notice that's very similar to 4. For all x, the only difference between 8 and 4 is notice that for all x, where x is not that special symbol 0. Where x isn't that special symbol 0, there exists some y such that their product gives us identity. Good? Okay? And then rule number 10 tells us what to do when we see multiplication and addition together. It says that if you see if you multiply by a sum, that is the same thing as taking a sum of those multiplications. And I guess I can put parentheses right here to help make that very clear. X times y plus z is identical with x times y plus x times z. Good? And then finally, the non-trivial assumption is what's called the non-trivial axiom. 1 and 0 are different numbers. They're not the same thing. Notice that if I didn't have this one, then I could just have a set with just 0 in it, and it would satisfy all these properties by itself. So the fact that 1 and 0 are different numbers is the key ingredient to making so that R doesn't just contain one element in it. There's actual multiple elements in there. So 1's not equal to 0, that's our final assumption. Those ones make sense?
Yeah.
Okay, now remind ourselves of some basic ways we can start coming up with some different numbers. We talked about this a little bit last time. Talking about, okay, so I know that 1's in there. I know 1's in R, whatever this set R is, with all its elements. I know that 1 is a member of R. And I know that anytime I have a real number, and I sum it with another real number, that thing has to be in R. That was one of our assumptions. Anytime you add two things together, they also have to be in R. If those two things come from R, they have to be in R. That thing's in R, that thing's in R. Therefore, when I sum those two things together, that has to be in R. Right? And so we wanted to do something like show that 1 plus 1 is actually something different from just 1. How do I know that 1 plus 1 isn't secretly just 1? And so we can validate something like that and make sure that's not. Let's see if 1 plus 1 is equal to 1. That's a question mark. I'm not saying that they're equal. Let's see if this leads to a problem. Let's see if we can prove that this is in fact different from this. Well, if 1 plus 1 is equal to 1, what do I know? I know that for any real number, I know that there exists, I'll call it y, such that 1 plus y is equal to 0. That's using this axiom right here, axiom 4. From axiom 4, I know that for any real number, there exists some other number, call it y, such that x plus y equals 0. 1's a real number. Therefore, there has to exist some other number, I don't know what it is, but something in this set, such that when I add the two together, I get 0. So this is from axiom 4 that we know that this is the case. So then, from logic, I know that 1 plus 1 plus y is equal to 1 plus y. I can put plus y on both sides. That was using that first theorem of logic that we proved. Not a theorem of mathematics. It has nothing to do with these axioms. That's going clear back to those first two theorems of logic that we proved. So 1 plus 1 plus y is equal to 1 plus y. Well, I know that this is the same thing as 1 plus y is equal to 1 plus y. That's using associativity on addition.
Okay, this is really bad because I missed the first lecture, but I'm not down, okay, with that.
With which part?
1 plus 1 plus y being equal to 1 plus y.
I'm not. I'm showing that this is a bad picture. Bad.
Oh,
Showing this does not work.
okay. Yeah.
I'm showing that 1 plus 1 is in fact not the same thing as 1.
Okay, sorry.
Okay, so this is a bad picture. So if this were true, if that were true, then we would have this, then we would have this, then we would have this. But I know that 1 plus y is equal to what?
0.
0. So then I have 1 plus 0 is equal to 0. I know that 1 plus 0, 0 is the additive identity. Anything added with 0 just gives me back that thing. And I get 1 equals 0. Uh-oh, axiom 10 says 1 is not equal to 0. Therefore, this is a bad worldview. 1 plus 1 is in fact not equal to 1. And I can do something similar to show that 1 plus 1 is in fact not equal to 0. So 1 plus 1 isn't 1, 1 plus 1 isn't 0. Therefore, this is a new real number that we haven't listed. So, we have a new number. We got to come up with some new random symbol for that number. We'll use that symbol. And we'll call that 1 plus 1. And so now we have, no, that 2 is in there. Just from these rules. 1 plus 1 is a brand new number, and it is a number. And we can do something similar for 3. So I can define 3 now to be 2 plus 1, and I can show that it's a new number. And so 3 is in there, and 4, and 5, and 6. And now I can show that all your natural numbers are in there so far.
Okay, but 1 plus 0 does not equal 0. It equals 1.
Yeah, 1 plus 0 equals 1. 1 plus 0, I replace that with 1. Remember, bad proof. Bad. I was showing that this leads to a bad worldview.
Yeah. I was thinking, solve that equation and substitute it for the 0 down there. And
I was just replacing on this side every time, and then just replacing on this side every time.
okay.
But every time, it turns out that's not true, so 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 that's not true. Oops. That was a definition for y. That doesn't make sense to put 1 to that. So that's not true, so that's not true. Because this being true makes this true, makes this true, makes this true, makes this true, but we know that this is false. And that's essentially how you do a proof by contradiction. You assume some statement, show that leads to some false worldview, therefore your assumption, 1 plus 1 equals 1, must have been false. Common proof style. Okay, but now you get a feel for how we can start generating all our natural numbers, and show that all our natural numbers are in fact numbers, and we can work with these things. And we now have definitions for basic numbers. A definition for 5, well that's 4 plus 1. Okay, what's the definition of 4? 3 plus 1. What's the definition of 3? 2 plus 1. What's the definition of 2? 1 plus 1. What's the definition of 1? Bad question. 1 is given its meaning through the axioms. You can't define everything. Otherwise you end up in an infinite regression, or you end up using circular reasoning. What gives 1 its meaning? Not a definition. The axioms do. The best answer to what's 1? It is the number that satisfies these axioms for that symbol.
So see, this is the basic problem I have. So we're just going to take these axioms and we're going to assume they're true.
We never call an axiom true in math. We say, what are the logical implications of those axioms? It's the difference between these two types of reasonings. One way I can say, if Socrates is a man, and if all men are mortal, then we can conclude, then Socrates is mortal. This we consider equivalents like it in mathematics are the types of statements we talk about. We never said Socrates is a man. We never said Socrates is mortal. We never said all men are mortal. We never said Socrates is mortal. What we said is if Socrates is a man and if all men are mortal, then Socrates is mortal. What we're saying isn't these statements are true, and what we're saying isn't that these statements are true. What we are saying is that these two statements imply this statement. That's the truth. We are not saying that this statement is true. We are saying that these statements imply all these other statements.
Why
That's
did
what's
anybody
true.
ever explain that back in the day?
What?
When I was going to school.
There's a big problem with
They
math.
just said it's...
There's a problem in math education where typically those who have a good fundamental understanding of mathematics go into mathematical fields, and those who fell out of a math degree go into math education. And so it's commonly the people teaching mathematics are the people who
They do not understand it.
don't have, I know, I would trust about 4 of the 5, or I would trust about 1 out of every 5 people I graduated with getting a major. 4 out of 5, I wouldn't trust their opinion on mathematics. Who graduated with degrees.
This is the problem I've always had, because the people who taught me math did not know what the hell they were talking about.
Nope, a lot of them don't. They don't know the foundations of axiomatic systems, and it confuses kids left and right, because eventually they're told, okay, there's geometry and there's hyperbolic geometries, and those two have contrary assumptions. And it's like, how can that be when they're supposed to be true?
So when you do a different field of math, you use a completely different set of axioms, right?
Yes, kind of.
Do you need to like redefine what the numbers are in every single one?
No, because it turns out that they're logically equivalent. What we mean by a number, if we were developing like a number theory course, what I mean by the number 1, and what I mean by the number 1 if I'm developing a calculus course, it turns out those concepts are logically equivalent. And so there's multiple ways to derive these same theorems and prove these same theorems coming from different places. And so there's a special field of mathematics called set theory. And the job of set theory is to give a foundation to every field of mathematics. So we started out with these axioms, which are relatively high-level axioms. We started out, so here we are in algebra. Here we are in algebra. We started out with axioms kind of clear up here on this level. But really, there's another field called set theory. Here's set theory, and here's logic. And if we were being rigorous, we would have started out developing the field of logic, and we did a whole course on that. It's a whole course in and of itself, developing logic. And then there's another course called set theory where you use logic to derive set theory. And then you can take set theory and you can derive these things from set theory, and then these things imply these things. So there is a field, set theory, which is the foundations of both algebra, and then you can take another field like topology, completely different, but uses the same set theoretical axioms to construct both those fields from.
So here's the reason I'm here, if I could be so bold.
Go ahead.
Because there's a problem that exists in my mind, and I think it might be with 0.
Okay.
Okay? Let's say you take a pie.
Okay.
And you divide it into thirds,
Okay.
right? 1/3 plus 1/3 plus 1/3 equals 1.
Okay.
But if you express that numerically, then you're going to say 0.333333 plus 0.33333 plus 0.3333 equals 0.9999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999 it looks like that is equal to 1.
It is.
Okay, so can you help me with that? Because I have a problem with that.
Sure.
I don't like it.
Well, we're kind of jumping ahead, but sure, we can do that real quick.
Is this ahead?
It's ahead, but I can give you the general idea. We just can't do it very rigorously. So let's say that x is equal to 0.9 repeating. So then 10x is equal to 9.9 repeating. Take 10x, I may take this equation and minus this equation. 10x minus x gives me 9x is equal to 9 with 9 repeating minus 9 repeating, just leaves me the 9, x equals 1. So when I define x at, it's still that. So 0.99 repeating is identical with 1.
Is that a glitch in the system?
No?
It looks like 1 to me.
Think about the way that Adrian just said before. You know that 1/3 plus 1/3 plus 1/3 is equal to 1, which is identical with 3 repeating, 3 repeating, 3 repeating is equal to 1. You also know that if you add those together, that's also equal to 9 repeating.
So, then, does that mean that like one has like another number that equals the same thing as it? So like.
That is identical number. It's saying 1 is equal to that is like saying 1 is equal to 2 minus 1. It's a different way of writing the same symbol.
Okay.
I could write, 58 over, what is that, 27?
But you wouldn't call 1 an irrational number.
No, this isn't irrational. An irrational number is a number whose decimal place repeats forever with, an irrational number is a number with infinite decimal places with no repeating pattern.
No repeating pattern, okay.
Yes.
Sorry, so what do you call it with repeating pattern? Just you call it that?
If it has a repeating pattern, it's a rational number. So 1's a rational number because it has a repeating pattern. The reals we can split into rational and irrational. If it has a repeating pattern, it's rational.
So-
If it doesn't, it's irrational.
Okay, so pi is irrational,
Correct.
that is rational,
Correct.
okay. Well, how in the hell? I've been thinking about this for a long time, and I just don't like it.
Yeah, there's a lot of natural discomfort when we're talking about infinities. Because you think about this as you might say this with infinitely many numbers, infinitely many nines. And to get comfortable with the concept of infinity, there's no real way to get comfortable with it other than to take the classes working with it, which would be a real analysis class, where you start nailing down exactly what you mean by these concepts and stop using vague terms like goes on forever and lay it out exactly what you are talking about. And so that's a real analysis class, which we've already done before. I mean, we can do that after this if that's what people want to do, but
Probably, I mean, the set theory thing is attractive to me.
Yeah,
Because this
that's a
is
ton
a
of fun.
set theory problem in my mind. Is this not a set theory problem?
No. I mean, it's a set theory problem if you want to think about
It's incongruous.
the infinity of the naturals being a set theory problem. Because you construct the naturals with set theory, but that's where you end, which are the numbers 0, 1, 2, 3, 4, etc. After that, you've kind of stepped into the field of now algebra.
Okay,
All right. So let's see. We went over all the axioms. We went over some basic notions now for how we're already well on our way to getting set up with the real numbers that we know and love. And we talked about how we can now define any natural number with the exception of 0 and 1. Those are given their meaning through the axioms. Any other natural number, we now have a definition for it, and we can know exactly what we mean by that symbol. And, well, no, we'll leave that for now. Okay. So now, let's start proving some of these theorems. I have them written in kind of dense form over there, so I'll rewrite them as we prove them over here, going over each one of those, making sure we understand. So our first proof is going to be that there exists one, maybe write it out, one and only one number in R such that one and only one number, number 0 in R such that x plus 0 is equal to x. Prove that there's only one thing in the real numbers that behaves like 0. There's only one additive identity. I'm going to do this by proof. I'm going to do this one proof by way of contradiction. So I'm going to say assume, and then this is such common terminology that we just use 4 letters for it. Assume by way of contradiction. Assume by way of contradiction that there exists, that's the there exists symbol, there exists some other number, 0 prime I'll call it, some other number, in, that's the in symbol, R. Slowly try and get you comfortable with this dense notation. Assume by way of contradiction that there exists 0 prime in R such that x plus 0 prime is also equal to x. So the 0 prime behaves like 0, and 0 prime is something different from 0.
can you help me understand what prime means here?
It just means a different symbol. I could have just easily used triangle
Then why
for the
didn't you?
symbol.
What means prime?
It's just our way of saying something different from the symbol I have written here. If I want to talk about something that behaves like 0 but isn't 0, 0 prime is common notation. It doesn't mean anything, it's just
Is there something that behaves like 0 that isn't 0?
No, that's what we're proving. So we're assuming by way of contradiction that there exists something out there, we'll call it triangle, in R such that x plus triangle just gives you back x. Or in other words, triangle behaves like 0.
Okay,
And we're going to show that leads to an impossible worldview.
okay.
Okay. So 2.
I guess this is why I don't like 0, because, you know, I believe in Copernicus, and there is not a center of the universe, and we're definitely not it if there is. And so this 0 business really bothers me.
So you're kind of getting into physics a little bit there with Galileo's principle of relativity. And yes, position is relative. It doesn't make any sense to say that my coordinate system, what I call 0, when I'm mapping out the universe, is superior to your coordinate system when you're mapping out the universe.
That is right.
And what I call 0 and what you call 0 is completely,
They're different.
they're different, but they
And so
have
now
no
we have this
effect.
problem exactly.
This has nothing to do with this universe.
Okay, yes it does, because there's an alien dude out there somewhere trying to get here. And he's gonna plot his course, and he's gonna use a mathematical system to do that. And we're trying to get there, and we're gonna use a mathematical system to do that. Okay? Those systems will ostensibly include 0. Well, now we have a big goddamn problem, right? Because this doesn't work.
In developing the field of math, you're allowed to use logic. In developing the field of logic, you are not allowed to use math. Bad. You
Okay.
cannot use math to define any notion in logic. You can only use logic to define notions in math. Similarly, we can use math to define physics. You cannot use physics, laws of this universe, anything that has to do with particulars of this universe, to dictate to math.
Because it doesn't work.
It's not even a matter of if it works or if it doesn't work. It's all physics presupposes math. Math makes nothing here says anything about our universe.
Well, I guess I'm making an assumption. I'm assuming that this should translate, math should translate to some correlation in the real world.
Some does, some doesn't. You have math, and maybe this is the part that happens to be useful for describing our world. Maybe it happens to be useful for describing our world, maybe it doesn't. But math couldn't care less about what our universe is like. Math is just math. You're just looking at, if these are true, what else is true?
Well, it's so elegant though, one would like to think that it...
Yeah, it turns out to be absurdly useful in describing our universe. And sometimes we're technically wrong.
Can that be accidental? Probably not.
Can it be accidental? Accidentally? You're saying, is it an accident that math is absurdly useful at describing our universe?
Yes.
No, it's not accidental since it's all built on logic, and the way we are, we can't help but think but through logic. And so anytime we're applying math, it's just a nice, really dense way of applying a lot of logic really quick. That's all it's doing. Logic is the only way we know how to reason. So when we reason about our universe, math is absurdly useful because it's a really dense way of doing a lot of this.
Is there a way to make this work without 0? You're pretty smart
I
guy,
mean-
so
Sure, we can call that thing something else,
just call it something else, but it's gonna be there.
but it's going to operate how it's going. The way these things say 0 operates is the way these things say 0 operates.
I just don't like the idea of in an infinite system we have a point of origin. That doesn't make sense.
We have a point of origin, but when it comes to physics, that point of origin is relative.
Sure, when it comes to physics, now we're just gonna talk about math.
All right, just
How
in
in
math,
an
what do you mean
infinite
origin?
system, A
So-
number line, a number line.
What number line? We haven't said anything about a number line.
Can we do that
You're
next?
trying to take your notion of distance, put that like this, and put 0 on it. You're trying to.
Yeah,
What you're really trying to do is
yeah,
force
well,
geometry into our system now.
Kind of, but I'm honestly trying to understand this.
No,
because,
I get what you're saying, but
I mean,
so the notion of 0 on a number line, the notion of a number line, you're already trying to force me to use geometry now. Because we can't talk about a
I'm
line.
not a bad guy.
No,
And
I'm not
it's I'm
saying.
not, I won't force you.
Okay.
But tie you up, and no chains, nothing.
Okay, let's try this again. The field of algebra and the field of geometry are distinct separate fields. When you bring those two fields together, that's called analytic geometry.
Which?
Analytic
Okay.
geometry. And so we cannot, with our axioms, give notions to things like lines. We have no notion of a line in geometry. So we have no notion of the real number line.
You mean in algebra?
In algebra, sorry, not sure what I said.
Okay.
So in algebra, no notion of a line exists with how we're using 0 here.
Okay. Okay.
And then the origin just turns out to be the name of a point. You choose to call some point the 0 point. You could have easily just called it the 100 point. Doesn't change anything.
It kind of does.
No, not for the way this universe operates.
No, for these properties of 0.
For these properties of 0, but I'm saying when you go back to thinking about the real number lines, so if you go back to physics, when we're trying to impose some coordinate system on our universe, then how you impose that coordinate system has no bearing in the math, how it all comes out in the end.
So my 5th grade math teacher was the volleyball teacher.
Okay.
Okay, this is the problem I have because she was an imbecile and could not answer this question. You're smart, so.
So you notice, I mean, I get to
Sort
prove
this
it to
out.
some of these
Sort this
kids.
out.
When I prove it to some of these kids, one of the things we specifically do is when we're solving a physics problem, I'll choose one coordinate system, and I'll choose a completely other arbitrary coordinate system just randomly to show how in the math, your choice of coordinate system, it completely just cancels itself out. And so your coordinate system doesn't matter in describing physical laws. And anytime you try to switch it around, however you choose that coordinate system ends up just canceling out in the mathematics. Because it turns out when this thing's flying through the air, it could care less what I call 0. And so it doesn't matter what I call 0. When I throw that thing through the air, if I try and describe it one way, I try and describe it another way. Any time I try to describe, using mathematics, some quantitative, some measurable property of the universe, turns out it doesn't matter what coordinate system I use.
Is that true?
Yes. Yep.
You swear?
I swear that it is a foundationally accepted property of classical mechanics.
Okay. Yeah, we have a problem with 0. Okay.
It's not the problem with 0 that I'm worried about. It's that there's still some physics that isn't known, and your intuition can go out the window, as we've seen with both Einstein's theory of relativity and quantum mechanics. Intuition can go out the window. So the best we can tell right now, modern physics, your coordinate system doesn't matter, and it always cancels out.
Okay.
If physics evolves, maybe it does matter. It makes 0 sense to me, but I can't promise that it wouldn't. Okay, so we're going to prove that there's only one number in R. Oh, we erased where we were drawing it because we were drawing it there. But so we knew that there were some things in R. In particularly, we know in R, whatever set this is, we know it has a 0 thing in there. We're going to prove that there's nothing else in R, there's no other symbol that we could eventually get to that behaves the same way as 0, that satisfies this axiom. 0 is the only thing that satisfies axiom 3, is another way that you could state what it is that we're proving. So we're going to assume by way of contradiction, meaning we're going to lead to a bad worldview, assume by way of contradiction that there exists some other number that we eventually get here, we'll call it triangle, such that x plus triangle also gives you x, and that triangle is something different from 0. It's not the same thing as 0. So then, let's see, what do I know? Then, there exists, I'll keep using y for it for now, then there exists a y in R, such that triangle plus y is equal to 0. This is using, which axiom is that using? 4? Axiom 4. Axiom 4 says that for any real number, there exists something else such that when you add them together, you get 0. Oh, that's not how I want to do this. Sorry. Not using 0 prime throwing me off. Okay.
Do your thing. Don't
No,
worry
it's
about me.
fine.
I
I shouldn't create a dependence on a
no,
symbol
just
under
do
proof.
your thing.
So then we know that triangle,
Call it delta.
delta, is equal to delta plus 0. Okay, how do I know that delta is equal to delta plus 0? I know that anything plus 0 is that same thing. So this is from axiom 3. I know that delta is equal to delta plus 0, right? Now I know from axiom 2, or axiom 1, that delta plus 0 is the same thing as 0 plus delta. Addition is commutative. I can change the order.
Okay.
And now I know, from assumption, that anything plus delta just gives me that thing. That's why I assumed delta to be. Delta was a mystical number, such that anything plus delta gives you back that same thing. So anything plus delta gives you back that same thing, 0. So I got delta is equal to 0. And this is a contradiction. Here's what we typically draw, back and forth arrows pointing at each other, to imply we just came to a contradiction. We said delta is not equal to 0. Here we said delta is equal to 0. Contradiction. 3. Therefore, our assumption is wrong. Therefore, there is no such delta. There is no such delta. There is nothing else. There is no other real number I can find such that anything plus that real number gives me back that same thing. So 0 is the one and only additive identity element. There isn't another one. That proof makes sense? All right, next one. Next one, we're going to prove that if x plus z is equal to y plus z, then x is equal to y. So try it out up here. We're going to prove that for all x, y, and z in the real numbers, x plus y equal to x plus z. Is that the way I wrote it there?
No, y plus z.
Oh, I got rid of the z's. X plus z equal to y plus z. X plus z equal to y plus z implies x equal to y. You understand the statement we're trying to prove?
Mm-hmm.
Good? Alright, so 1. How do we prove an if-then statement? How do we prove an implication? We assume the antecedent and show that implies the conclusion. So let x, y, z, and r, let x, y, and z be real numbers such that x plus z is equal to y plus z. Good so far? Pick any 3 random numbers in the real numbers that satisfy this property. We're going to show that any 3 numbers that happen to satisfy this property, then the 2 of them that we call x and y will satisfy this property. That's pretty much what we're doing. 2. Then there exists, what should we call it? Yes, W. We haven't used W. Then there exists W in R, such that z plus W is equal to 0. What axiom am I using there?
3. I mean 4.
Axiom 4. Axiom 4. Axiom 4 tells me that for any real number, z is a real number, there exists some other real number, we're going to call it W, such that their sum produces 0. Then, using logic, not math, x plus z plus W is equal to y plus z plus W. That's using logic. 4. Then x plus z plus W is equal to y plus z plus W. That's using axiom
2.
2. Thanks. Axiom 2. Addition is associative. So rather than associating those 2 terms together, I associated those 2 terms together. But now, what do I know? What is z plus W?
0.
0. So then, x plus 0 is equal to y plus 0. Which gives me that x is equal to y. And we're done. That's what we were after. We were trying to show that if we found 3 numbers, x, y, and z, such that x plus z is equal to y plus z, then those same 3 numbers satisfy this condition. Namely, x is equal to y. And we call that the right-hand cancellation rule. So you can cancel out with some on both sides of the right hand, or on the right-hand side. Okay, that was theorem 2. Theorem 3, I guess we don't have to erase every time, keep writing down. Theorem 3, we're going to do a proof that for all x in R, x times 0 is equal to 0. So any number times 0 is equal to 0 is what we're going to prove here. So 1,
Can you help me out with this one too?
with the,
This is another one I don't like.
well, we're going to prove it. X times 0 is equal to 0.
But you're gonna do it by using rules that are kind of nefarious. These are, well, I shouldn't ask questions when I didn't attend the class where you built these axioms.
We did not build these axioms.
You didn't build them from logic?
To build those axioms would require us to go through set theory. You have to use set theory to build these axioms and use the axioms of set theory.
I need to be in the class where you built the axioms.
We have never built all those axioms before in a set theory class. When I did set theory, I built axioms for building topology, not algebra. But they're out there. They're called Pino's axioms, are the set theory ones, and they build up to algebra.
So the basic problem I have, maybe we don't need to go through all that, but is probably from this assumption that I've carried that all of algebra specifically, but math, is really moving back and forth on the number line. So it's more or less shorthand addition. And I don't know how you get any number multiplied by 0 equals 0 when this is the thing I've had in my mind, it's shorthand addition.
So
That doesn't work.
displacement on the number line, if you want to think about it as shifting on the number line, you
That's
have
how
to.
I think about it.
Oh,
Is that?
no, that's
the way
fine.
to think about it?
So you can think about it as shifting, but you can't just think about shifting. You have to think about shifting the number line and scaling the number line.
Okay, and what means that?
So scaling the number line, let's say that I've got some section of the number line here, and we'll just say from 0 to 2.
Okay,
Multiplication is rescaling the number line. If I multiply by 4, then the way we think about that geometrically is stretching this out by a factor of 4. And so then it would be from 0 to a.
mm-hmm.
Similarly, if I were to scale it by 0, that means scaling it down to a point. And that's actually, when you get to higher maths, think about it in terms of shifting and scaling is actually a very useful way to do it, especially when you get to the complex numbers. You can think about a lot of math as just rotating, shifting, and scaling. And it's very useful because the geometry just happens to match the same thing. It's amazing. As the operations.
So this multiplying a number by 0 and it being 0 is super, super, super legit.
Yes, every time your intuition for the number 0 should satisfy that, as well as any foundation you build for the number 0 is going to satisfy that.
Well, I know it does by the rules, but I don't like it because, like the previous example you gave, 5 times 5 is 5 plus 5 plus 5 plus 5 plus 5, right? Did I miss a 5? Whatever, you
That's right.
know what I mean.
Yeah.
Do that with that.
X times 0 is x 0 times.
Exactly. So you take a real number that exists and it represents something that is real. Let's say you take 6,
Okay.
and that number represents 6 actual pies that
Okay.
exist, that are on this table,
Okay.
okay? And you multiply that by 0, the pies stay, they exist, and they're represented by the number 6. I didn't multiply it by,
Well, you have to accept a change in the system if you think about multiplies that way, because do a different number. Say you have 6 pies. well, you multiply it by 4, you still have 6 pi's. Now if you want to say, well, if I had 4 groups of these 6 pi's, then I'd have 24 pi's. Similarly, I could say if I had 0 groups of these 6 pi's, I'd have 0 pi's. There's 6 pi's sitting in the store. I give you 0 groups of those 6 pi's. How many pi's did you purchase? None.
0 groups. Okay, I'm down with that. Okay.
Alright. So any number times 0 is equal to 0. Let's see if we can prove it. Not sure how I'm going to go about this one yet. Maybe something like this. But let me play over here for a second. Okay, I got an idea in my head. Okay, so observe that 0 is equal to 0 plus 0, right? Good with that? So 2, then x times 0 is equal to x times 0. Good? And then we can distribute through using this axiom. This axiom tells us anytime we have those 3 numbers, x, y, z, is going to be x times y plus x times z. So this is equal to x times y plus x times z, looking at this axiom. So we just use axiom 9. You with me?
Yeah.
Okay. So then we have that x times 0 plus 0. If I add 0 to this, it didn't change anything. Good with that? So I kept this side the same. And I'm going to keep this side the same. Just keep it as x times 0 plus x times 0. You good with that?
Yeah.
Finally, I'm going to swap the order on these. Remember that from axiom 1, addition is commutative. So I can write 0 plus x times 0 is equal to x times 0 plus x times 0. Now, using our previous proof, I knew that if I had x plus z is equal to y plus z, then those 2 left-hand things have to be the same. I have x plus z is equal to y plus z, therefore x and y have to be the same. Or I can cancel out that side, that element on both sides, if you prefer to think about it that way now. In either case, we get 0 now is equal to x times 0. Once again, I know that multiplication is commutative, so this is also equal to 0 times x. So it doesn't matter what side we put the number on, 0 times x or x times 0, it always comes out 0. And we're done. Any questions on that one?
Why was it important to switch the order at the end?
Just to prove it.
To show you that no matter what side the 0 is on, when you multiply by 0, you just get 0. You're so used to, the 2 operations you're the most used to working with are multiplication and addition, which happen to both be commutative and associative. And so in your mind, you think it's kind of redundant that I keep specifying which side the symbol's on, whether it's x times 0 or 0 times x. To your mind, that just seems so trivial to pretend that those are the same. Why would I bother saying it? And that's a comfort that you have working with this system. Because that is not always the case. For example, you might have already come across function composition. Function composition is not commutative. F composed with g is not the same thing as g composed with, oh, you did come across that. Yeah, we proved that in calculus. So there's tons of operations out there that aren't commutative, and there's tons that aren't associative. It turns out that multiplication and addition are both those things, and so you're very comfortable using those. But there's plenty of operations that aren't that way. So it might seem like a lot of overhead, but that's a comfort thing. That's not because it is too much overhead. Anything else on those? And even sometimes I forget to take the time to specify the difference because I'm in the same boat that you are. Too comfortable. Let's see. We just barely proved that anything times 0 is equal to 0. All right, let's try the next one. Let's show that for any 2 numbers, if their product is 0, then one of the 2 numbers has to be 0. That's kind of an interesting one.
Why do we like these theorems?
So let me rewrite this out. You know, it seems like a lot of overhead, but it really helps spend the point home. If Socrates is a man, and if all men are mortal, then Socrates is mortal. So this happens to be one statement that we can conclude from these two. We'll call them axioms. Here's our two axioms, axiom 1, axiom 2. From these two, we're able to derive this other conclusion. Now here we're working with more statements, and so we're going to have 10 statements in our if column, and our thens are going to be a huge list of theorems. There's going to be thousands of them that we can derive from just these 10 things being true.
Okay.
So then we go out to some field in somewhere in the real world. It's harder to work with these than with geometry. Geometry's, there's a reason it's the base class that they use for proving. So let's briefly get some intuition for some postulates in geometry. So postulate 1 in geometry is 2 points, define a line segment. I won't write it out, but if you have 2 points, we can create a line segment through those 2 points. Another proposition 2 of geometry is if I have a line segment, I can extend it as far as I want.
So a postulate is the same thing as an
As axioms, sorry. Let me call them axioms. I shouldn't call them
That's
postulates.
fine.
As axioms?
Axioms.
Postulates is the same thing.
Yeah. Okay, axiom 3 tells us that if I have a line segment, I can pick the point, call it the center, and pick that other point and create a circle with it. Axiom 4 says all right angles are congruent. If I have a right angle, it's congruent to any other right angle you find. And then axiom 5, it's the weirdest of them, but it's the last of them. So axiom 5 says, if I have a line and a point not on the line, there exists one and only one line I can draw through that point such that these two lines never intersect. That's not the parallel postulate. Okay, so those 5 axioms, those are the only axioms in Euclidean geometry.
Okay.
And so what we do, and then we prove tons of things that happen to follow from just these 5 things being true. If these 5 things are true, then we get all the theorems for free. They apply those theorems. So then we go out in the real world, and here I am in the real world, and I test. Does it feel like in this space that I'm in right now, that if I have 2 points, I can connect them with a line segment? Yeah. Does it feel like I can extend? So we test these now in some scientific field, like actual physics. I say, in our universe, does it seem like this is the case? Yep. Does it seem like this is the case? Yep. This, yep, this, yep, this, yep. Now I get all the theorems of geometry for free. And I don't have to go reprove them for my special space that I'm working with. So similarly, we construct other spaces virtually with computers, and we prove things that happen to be true in a bunch of different spaces. I accept some computer space where it satisfies these properties. So now I know in that space, all the theorems come for free. And I don't have to go rederive them for that special case. So we have tons of different areas where we use different fields of math. And if we can find some area and it looks like it satisfies some axioms for some field of math, we get the whole field of math for free. And we don't have to rework it. Okay, so next proof, we're going to prove that if x times y is equal to 0, then x is equal to 0 or y is equal to 0. Now I'm going to start getting a little bit lazy here, and that's going to happen throughout the class goes on. We get lazier and lazier, and more is just implied that you're going to understand what I'm saying. When I say if x times y is equal to 0, then x equals 0 or y equals 0, in your mind, you should infer that I'm saying that for all real numbers x and y, if x times y is equal to 0, then x is equal to 0 or y is equal to 0. And I'm going to stop specifying for all real numbers over and over again. So that's going to be the next piece of laziness that I'm now going to drop, saying for all real numbers over and over again. All right, so let's prove this statement. It's an if-then statement. We assume the antecedent and show that implies a conclusion. So let x and y be real numbers such that x times y is equal to 0. What's our job? Our job is to prove that either x equals 0 or y equals 0. Right?
Yeah.
2. if x equals 0, notice there's one of two cases, x is equal to 0 or it's not equal to 0, right? So if x equals 0, then we're done. So now we're just going to consider the case where x isn't equal to 0. 3, if x is not equal to 0, now we're going to continue and show that implies y is equal to 0. And so we've handled both cases, because either x is 0 or it's not 0. If x is 0, then we've shown that x or y is 0. If x isn't 0, we're going to show this ultimately implies y is 0, and therefore we've shown x or y is 0. Make sense?
Yeah.
That's big picture how we're going at this. So if x is not equal to 0, then there exists some number out there. We already have a y, so should we use z? Then there exists some number z in R such that x times z is equal to 1. Okay.
This is another problem. I hate to belabor the point.
You're fine.
But if we're moving stuff around on a number line, okay, and I'm trying to wrap my mind around the scaling the number line. But if we're moving stuff around, it just seems like you should be able to get to 0 without using 0 to get to 0. It seems
If
like
you're
you should be
shifting,
able
you
to
can.
do that.
If I want to get to 0 from 4, the shift I apply is -4.
Yeah, so this bit here is implying in my mind, maybe I don't understand it, that you can't get to 0 without using 0 in a multiplication scenario.
Alright, let's try and remember. So the words I use for you is groups. Okay, so this is saying, if you have x groups of y objects, and it turns out that the total number of objects you have is 0, then either the number of groups you used was 0, or each group contained 0 items in them.
Okay, sorry, I forgot about that bit.
Okay,
And that's important.
yes, making it click with your intuition is huge.
Sorry. The group thing, that's new.
Whatever works. I tell people the hardest part about teaching is saying the same thing 5 different ways. Because something just appeals to the intuition. And so,
Well, that's hanky, right? I mean,
it's hinky, but it's so hard to have a rigorous understanding of something before you get the intuition. So you get the intuition, you accept, okay, the intuition, yeah, it's not precise, but the famous mathematician says, never try to prove something until it feels like it's almost obvious. Then actually sit down and try to prove it. So that first step of making it almost obvious what you're saying, making that intuition click so it's almost obvious, then you're ready to go about trying to prove it. But until then, you go try to prove something, you'll just be stuck. So that intuition, that's the hard part. Because everything else just falls from the rules. So getting that intuition to stick, that's the hard part of my job. Sometimes proofs are hard, because I have to make the intuition stick in my own head. Okay, so re-stepping through this. Okay, so we said if x is equal to 0, then we're already done, because we need to show that one of those two is 0. If x is not equal to 0, then we know from axiom 7 here, oh, not axiom 7, axiom 8, for any number where that number isn't 0, there exists some other number such that their product equals 1. So since x is not equal to 0, then I know that there exists some other number out there, I'm just calling it z, such that their product is equal to 1. Okay, good? So then, remember I know that x times y is equal to 0, so I'm going to multiply z to both sides using logic. So then I'll put the z in the front, order doesn't matter on those. I'll hope that you're okay with the fact that I'm just use commutativity behind the scenes. We're multiplied to the left side, and then we're still using logic, since I put both on the same side, so never mind. So then z times that symbol is equal to z times that symbol. You with me?
Yeah.
Okay. Over here I'm going to use associativity. So I'm going to rewrite the same equal sign. Over here I'm using associativity, so I have z times x times y is equal to, what is z times 0?
0.
0. We just barely proved anything times 0 is 0. Furthermore, what's z times x?
1,
1. How did he come up with that?
because x times z.
Our definition of z. What is z? It's the magical real number such that x times z gives you 1. So I know x times z is 1 times y is equal to 0. 1 times y, by definition of the multiplicative identity, is y. Y is equal to 0, and we're done. So I just barely showed, if x is equal to 0, then x or y was equal to 0. And then I showed if x wasn't equal to 0, then y was equal to 0. So x or y was equal to 0. Any questions on that proof? The logic following?
Yeah.
Good. Okay, so that was Theorem 4. Theorem 5, proving that the additive inverse is unique. Alright. This one I'm going to put back in the for all since there's a exist. So next, what am I going to prove? I'm going to prove that for all x, there exists one and only one. When you put the exclamation point after the there exists symbol, that means one and only one. So there exists one and only one y such that x plus y is equal to 0. For every x, there exists one and only one y such that their sum produces 0. Intuitively, let's get a sense for what we're saying intuitively, and then we'll go back to this proof. If x equals 4, then what's my one and only one y?
Can I ask a notation question?
Yes.
So what, because you see these numbers and symbols and everything, how is one supposed to know when a parentheses means such that?
So anytime you have a there exists quantifier,
Okay,
after you read that one, in English, you say such that before you go to the next set of parentheses. So it's when it follows an existential.
okay,
So that's the rule with that.
it's just a thing,
Yeah, it's the way to convert to English.
okay.
Makes it read nice. Okay, so let's get a feel for what the statement is saying. So we're saying that for any x there exists one and only one y slash your sum is 0. So if our x was 4, the one and only one y I can add to x to get 0 would have been
Negative 4.
-4. Let's try one more corner case. What about if x were 0? What's the one and only one thing I can add to it to get 0? 0. Okay, so I think you gotta get a feel for it. Let's actually prove this now. So, 1, let x be any real number. Let x and y in R. Let x and y in R such that x plus y is equal to 0. 2. Assume, by way of contradiction, we're going to set up a bad worldview here. Assume by way of contradiction that there exists some other number out there, some other number, we'll call it y prime. There exists some other number in the real numbers such that x plus y prime is also equal to 0, but y and y prime are different numbers. This is impossible. We're going to show that if x plus y prime equals 0, then y prime is in fact equal to y. So we're setting up an impossible worldview. We're going to show it's impossible. Make sense? So 3. So then, let's see, how do I want to do this? So then, I know that y is equal to y plus 0. Good? And I know that 0 is the same thing as x plus y prime. So y plus 0, good?
Yeah.
Is equal to associativity y plus x plus y prime. And what is y plus y prime? What's y plus x?
0.
0. Plus y prime, which 0 plus anything just returns that thing, y prime. So I just barely showed that y is equal to y prime. Contradiction. We said y is not equal to y prime. Here we got y is equal to y prime. That's a contradiction. We set up a bad worldview. Therefore, our assumption that there does exist a y prime was impossible. Therefore, y prime does not exist. Or another way we could have said that, therefore, y is unique. There's one and only one y that satisfies that equation up there. Those both make sense?
Have we defined negative numbers yet?
No. Now we can finally define a negative number. Remember, a definition doesn't make sense unless it tells me one and only one thing. It can't tell me multiple things, otherwise I'm not defining something. So now I can create a definition. Definition. What is negative x? Negative x, I define that to be the unique solution, the unique y such that x plus y is equal to 0. That one and only one y that satisfies that equation, we proved up here that there is one and only one y. So whatever that one and only one y is, that's what we mean by this symbol. Anytime you see negative x, what is that? That is the magic solution to the equation x plus y equals 0. It's the magic thing that you can plug in there, the magic number that goes in there that makes this true. So now we call that the additive inverse.
Okay, I have a question that's maybe a little tangential,
Go
but
ahead.
I'm trying to build my understanding from the bottom up. And it looks like to me that there is a really intimate relationship between multiplication and addition. And you can carry that through to subtraction, obviously, here,
Almost, yeah, we're getting there.
almost. But then when you take the inverse of multiplication or division, then that doesn't work. And it's an incongruity that I don't like. So
Yeah, it's
I'm
a bit
wondering if you
frustrating
can
that
solve that.
it falls from right here. It's this exception right here. So you'll notice the difference between 8 and 4. 8 and 4 say the exact same thing, one for multiplication, one for addition. The only difference is here we require that the x not be 0.
Yeah, because of all the zero Folderol.
And so that same criterion is what makes division not behave nicely. Because you can't divide by 0.
Yeah, why not?
Because 0 has no multiplicative inverse. We're going to
Because
define
somebody
division.
said so.
Huh?
Because somebody said so? Is there a logical reason why it doesn't?
I can give you some intuition for why we can't define defining by 0. If I try to say x divided by 0 is equal to something, if I try to define it to be something, b,
Well, okay, so you use your little grouping thing in the grocery store. That makes sense, kind of. It requires, I think, that you
Okay.
accept the definition of or as being inclusive, right?
or is always inclusive for.
Well, or is always inclusive.
Yeah.
So it's this group or this group, that kind of inclusiveness, right?
I don't know what you mean by the or groups.
What I mean is.
When we did multiplication, it didn't say or. So
Is
when
multiplying a number by 0 and it yielding 0 always demands that one of,
oh, when we're okay, I'm with you now.
are you down?
Yeah, you
Okay.
talk about the actual proof that we. Yeah, I'm with you.
And so, this is different.
This is different from that.
I don't like that. It seems like math should be the same.
Well, they're saying different things. We haven't defined division yet. That was just saying, one was just saying if a times b is equal to 0, then one of those numbers have to be 0. This one is saying x times b gives you 0. Well, no, it's not even saying that. This is saying, let's think about the right way to say this.
And is there in fact this intimacy in the relationship between multiplication and division that always works? They're not really separate functions, are they?
division is not separate.
Excuse me, multiplication and addition. They're actually not separate functions, are they?
You can define multiplication the way that you're thinking about from addition.
Okay,
There is a valid way to do that. Yes.
so that intimacy exists.
That intimacy exists.
Why doesn't it exist here?
It does.
You show me?
I'm not sure what you're asking me to show you. There is a way to define multiplication in terms of addition, and we define division in terms of multiplication, and we define subtraction in terms of addition. So division is really just a different form of multiplication, which you can think of as a way of performing addition.
Yeah, that is how I would think of it.
Okay.
And then when you get to dividing,
So when I say that A divided by B is equal to C, this is a way that we rewrite B times C is equal to A. This symbol only makes sense if we have a scenario where this is true. I can set scenarios where this isn't true, which then this no longer makes sense.
okay,
For example, I can't say that 3 times 0 is equal to A, or is equal to 2. Since that's not true, then if I tried to transpose that over here, then we would have ended up with, oh, I put the 0 in the wrong spot, but,
well, if division were truly an inverse operation of multiplication, then we wouldn't have all the drama around 0, would we?
if what?
So, division is just purely an inverse operation of multiplication, yes?
Correct.
Okay, and in multiplication, if you multiply a number by 0, you get 0. I don't like it, but going with it,
Okay.
then why can't you divide by 0?
Because to multiply, let's start with
Using
2.
the exact same logic
Let's-
with the groups and the pies and the stuff.
Let's use 2 for a second. So when I do x times 2, then that's just x times 2. If I try to do x divided by 2, then what that implicitly means is x times 2's multiplicative inverse, i.e. 1/2. So dividing by 2 is really multiplying by 1/2.
Yes.
It's multiplicative inverse. So it's not that just because you can multiply by it, you can divide by it. It's if you can multiply by it, then you can divide by its multiplicative inverse.
Okay,
But 0 doesn't have a multiplicative inverse.
why? It's a real number.
It's right here. The symbol 0 satisfies these rules. And one of the rules is that for any x where it's not 0, it's guaranteed to have a multiplicative inverse. 0 is not guaranteed to have a multiplicative inverse, and it doesn't have a multiplicative inverse.
Does that cause problems? It just doesn't seem like certain numbers should have exceptions. It seems like they should all behave the same way.
Tons of numbers behave very differently. 3 is prime, 4 is not. There's properties that come with that. I can divide 4 evenly into 2 integers. I can't do that to 3.
Well, who cares about integers? I'm talking about just.
But I'm saying it's a property of a number. 0 doesn't have a multiplicative inverse. 4 is not prime. 3 is prime. It's just a property. I mean, you're fine with there being different properties that only some numbers have but other ones don't, but you don't like the multiplicative inverse
Yeah,
one.
I kinda like prime numbers, that makes sense to me. But it's just a fun little thing. It's not like they're behaving differently in different situations. 0 behaving differently if you're multiplying than if you're dividing just seems really, really, really bad. And unless there's a logical reason why it should.
Well, I mean, this is the logical reason why it should. It's a number that doesn't have a multiplicative inverse.
But just because we said so, I'm talking about reality.
If
Somebody
you
said so over there, and I know you can say they said so.
if you
somebody
want
said
0
so.
to have a multiplicative identity, or a multiplicative inverse, I mean, then that would introduce division by 0 into your system.
Yes.
Once you allow division by 0 into your system is fundamentally broken.
Why?
So, quick example. Let's do b divided by 0 equals, let's say we want to assign it some number, call it c. Whatever it is. Let's pretend that's defined. Or even 1 if you want to pick a real number. 1 divided by 0, I want this to mean something. We'll call it c and see what property c has.
Okay.
Well, if we allow this to happen, then I have to allow that 1 is equal to c times 0. So I got c times 0 is equal to 1, but we already know c times 0 is equal to 0, and we already know that 1's not equal to 0.
I think somebody made a mistake with the rules. I'm not sure.
Well, the rules that we have work very well. We've used them a lot for a lot of things, and they're very useful. But, so this is why if you can't allow division by 0 to be anything, otherwise it creates a mess. And also, even if you think, okay, well, maybe that's for a number divided by 0, but why can't we do something like 0 divided by 0? Why can't we at least define that special case to be something like 0 or 1 or 2?
Yeah, these are questions I've asked myself because you can't just say something doesn't exist because it makes a mess. Maybe there is a mess.
No, it's not whether it exists or not. It's you can't introduce something into your system that allows logical contradictions to exist in your system. And so the logical contradiction we got when we went back to if we let 1 divided by 0 equal some number b, then we got 1 is equal to b times 0. There's a contradiction.
Just because of that other bullshit that 0 times any number is 0, but that only works if you have a very special grouping like
But
you're
it's
talking.
also a property you notice that you want 0 to have, even following your intuition. You want when I have 0 groups of 5 objects, I have 0 objects. Or if I have 5 groups of 0 objects, you want to have 0 objects. So your intuition wants 0, whatever that symbol is, to behave so that this is the case. I mean, when we were thinking about what's useful, we worked our way backwards to these rules and said, okay, these are the rules that give us those numbers that are so useful. And we tried to find the most limited set of rules we could go back to that still give us the numbers that are useful in the way we want them to be useful. And one of the things we want 0 to do is we want it to behave like this. And one of the things we want 1 to do is satisfy those properties. So we also want 0 to satisfy those properties, 1 to satisfy those properties. And it turns out if you want 0 to satisfy a property like this, then you can't allow it to have a multiplicative inverse. Otherwise it won't satisfy that property, which we just showed. If you allow division by 0, this property becomes broken. And your axioms become inconsistent. They imply 2 different things. From using some set of axioms, we got x times 0 is always equal to 0. And using another set of axioms, we got x times 0 is equal to 1. If we replace that with this.
Somebody should fix this.
So your system now has a contradiction, which is no longer an axiomatic system.
Yeah, somebody should fix this.
It was fixed. And the big fix is right there. That's the fix. So,
How did
0.
math work before they invented 0?
Geometry, so Euclidean geometry never has to use the number 0. And you can derive all of Euclidean geometry and prove a lot of the same things that we prove here without ever using 0. It's a very tedious way of doing mathematics, but we can prove the same things.
So why do we want 0?
Because it's useful. Because we can prove more things than we could just do in Euclidean geometry. So it gave us all of Euclidean geometry and then some. So it didn't get rid of any of geometry. So it turns out everything we wanted already from Euclidean geometry, we still got when we introduced 0 into the system. And we just expanded our system and included more things that happen to be useful. And 0 is a very useful number. And doing things like setting up coordinate systems is absurdly useful. Going and looking at how people did proofs before analytic geometry, and then afterwards, it's a night and day difference. Like if you try to go and read Galileo versus trying to read Isaac Newton, and they're not that far apart, like 100 years apart, what Galileo had to use this to talk about, Isaac Newton can now use this to talk about. It was so powerful to introduce the real number line to geometry, which included that number 0. And so it's just super useful. We're still proving all the same things. We haven't found something that you can prove if you don't use 0, that when you introduce 0, it's no longer the case. 0 just enabled us to do more and never got rid of anything that we already wanted.
Well, I guess the idea that you can describe physics with math, but you can't describe math with physics bothers me a little bit. But if that's true, then it just means we have a weakness in our number system.
It's a strength in the number system. It tells you it's an abstraction. This universe could cease to exist, and a whole new universe with completely different laws of physics could suddenly come into existence. And all the math that we use in this universe, we could still use in that one. Every theorem in that book would still be true. You could give it to some other being in some other universe with completely different physics, and all the math is still just as valid, and they can still use it. They find the set of axioms that seem like they describe their reality, their universe, their physics, and then just get all the theorems for free. So it's that abstraction, that there is no dependency on physics, that makes it so powerful. And it took a long time to get past that abstraction. Because when Euclid was developing his elements, he was just trying to describe physics. And so the big leap in mathematics, when you have a big explosion in mathematics, it's getting past that, that crutch of thinking math has to just describe this universe, and they have to be intimately related like this, rather than viewing there's math, and this is math that happens to describe our universe. That's one of the great revolutions in thought, is making that distinction. And it took a long time for people to make that distinction. Gauss was the first one to go about it. He's like 2,000 years after Euclid. Anyways, so yeah, if we allow division by 0, if we allow 0 to have a multiplicative inverse, it breaks our system. It allows contradictions into our system.
So we just say no.
Correct. We always say no to contradiction. Okay. So our next proof, so we define negative x. So now we know what we mean by negative x. I really like calling it negative x. I like calling it x's additive inverse, but we're used to negative x, so I'll use that terminology. But just know that an additive inverse isn't necessarily a negative number. If x is equal to negative 4, then the additive inverse of x is 4. Notice it's not necessarily a negative number. We typically use negative numbers to refer to numbers less than 0. So we'll call that negative x, but remember, what we really mean is the additive inverse of whatever x happens to be. Sometimes that's a negative number, sometimes that's a positive number. And don't get confused, just because you see a symbol negative x, that does not mean we're necessarily talking about a negative number. It means we're talking about the additive inverse of some number. Does that make sense? Important distinction. Okay, and so now we have negative numbers in our system. Notice that when we were building R, when we were writing out all the numbers we knew about R, we knew it had a 0, we knew it had a 1, we knew it had a 2, we knew it had a 3, and now we have negative numbers defined. We now have negative 1 defined, negative 2 defined, negative 3 defined, and we can go and define all those numbers. So now we can define not only the natural numbers, but now we can create valid definitions for all the integers from our system.
Okay.
Good? So what's the definition of negative 3? It's the additive inverse of 3. What's the definition of 3? 2 plus 1. What's the definition of 2? 1 plus 1. And 1's a number that's given to us from our axiom. So everything's well defined. I can give you precise definitions of any random number you decide to choose so far out of the positive integers. They're precisely defined exactly what they are. Alright, so our next one. Negative x is equal to x. I don't know. Get to the point where some of you could probably come and start doing these. Any of you guys want to try one? Negative. Some of you have had a lot of experience.
Yeah.
Yeah? You think you can do it?
No. I just have a lot of experience with it.
You have a lot of experience. Just because you don't see how to do it right out the door doesn't mean you can't do it. Remember, sometimes you just got to get there and start playing. You want to try it?
Yeah.
All right, come try it. So you're proving theorem 6.
Okay. can I do this as an implication proof? Or do I do this by way of contradiction?
I would show that negative x is just equal to x, so I keep messing with it. But
I'm saying would I go about the proof, proving it by way of contradiction, or just
No.
as an implication?
you can think about it as an implication. You can say if some number is equal to negative x, then that number is equal to x, is the way you can phrase that as an implication if you want.
Yeah,
So if
that's
y
how
is
I
equal
wanna do
to,
it.
alright, so you can say if y is equal to negative x, then y is equal to x.
Okay.
Okay, so if y is equal to negative x, what's the one property that for sure y satisfies?
If it's equal to that,
Yeah. So you know that y is equal to negative x.
then it's equal to the negative.
What is negative x? Describe that number to me.
It's the additive inverse. It's the additive inverse of x.
It's the additive inverse of x, or it's just the additive inverse of negative x. Right? Think about this, it's just the additive inverse of whatever that symbol is. Treat that like one symbol if that helps you for a second.
Okay, so wouldn't that just be so you're saying rewrite y?
Well, I'm asking you what you know about y.
Based off that definition?
Uh-huh.
Well, you can say there exists another number such that that equals negative x, which implies y is equal to negative z. But where does that mean?
No, you don't know that y is equal to negative z. You know that y plus z is equal to what?
That's just equal to negative, right?
Okay. Yeah, except for you gotta be a little bit careful with your symbols here. We don't have subtraction defined yet. Right?
Oh, I see.
So you substitute out your y and you substitute out your z. So you have negative this symbol plus that symbol equals what?
Negative that symbol plus that symbol is just negative that symbol.
If I have negative some symbol plus some symbol, what does that equal?
0.
0! That's the definition of what we mean by negative that symbol. It's the
Okay.
thing that cancels out that and gives us 0.
Yeah, I see where we're
Okay.
Okay. Then y plus z is just equal to 0, right? Or
Okay.
am I jumping the gun too much?
No, that's exactly right.
Trying to prove that y equals x. And that's the same thing as y plus negative x, which is equal to 0. No, I don't need to do that.
Yeah, you're kind of going in circles. I think your y's and z's are throwing you off a little bit.
Doesn't that just take me to the start?
You're kind of going in circles. So, start with this. Start with something that you already observed. So maybe we say 1, just something to point out even though you can use it. Observe that negative x plus, maybe I'll write negative x first. Negative x plus negative x is equal to 0, right?
Yes.
2. Then is equal to what?
The
Add
additive-
0 to it. Add 0 to this. Add 0 to that and keep manipulating that. You're going to keep manipulating this until you get is equal to x on the other side.
Yeah.
Okay. So what's a special 0 you can add to that?
Just the additive identity of that.
Okay. I don't think I'm stating it very well. So this is equal to negative x plus 0. Right?
Yes.
Let's rewrite that 0 now in a way that's useful.
Well, that's the same as that, right?
Right? But we don't want to use that substitution, otherwise we'll end up going in a circle. Is there another thing that we know adds to 0 using x's? What else equals 0? Just using x's.
What else equals 0 just using x's?
Negative x plus x.
Negative x plus x equals 0. So try substituting that with an x plus negative x and see where you go from there.
Okay.
Plus negative x.
Yes, you're right.
Wonderful.
Then where do you go from there?
I don't know. Can you group two of those together? In a
Yeah,
useful
but then
way?
you just have two of these.
So group those two and what do you get?
Right?
What? No, I don't know what you just said. No, you don't have two of those.
You do have two of these.
You have a negative x, and you have a
Yes.
negative x. So write those two right next to each other, and then write the plus x at the end.
Like that.
Sure. Now what does that equal?
This is too obvious, but I still don't see it.
Put brackets around your left-hand two terms. What is that number?
Isn't that 0?
I don't know. Look at line 1.
Okay.
Which is equal to?
X.
Which is just equal to x.
There you go. That's what you're after. You showed negative x is equal to x. Yeah, so caught up in the details, you're losing the big picture. Right?
Okay. Yep.
Negative x is, we added 0, which is x plus negative x. And there's two different ways that we can get 0 here. We can get negative x plus negative x is 0, and we also know that negative x plus x is equal to 0. We use those two facts, and we just combine those into one line, showing that negative x is equal to x. Make sense?
Yeah.
All right, someone else want to try one?
I don't know. It's like way too simple.
Yep, something about when you come up and do it, everything gets harder. The next one, giving a proof that -1 times x is equal to negative x. So let's prove that one. -1 times x is in fact negative x. How am I going to prove that -1 times x is equal to x? Maybe say something like this. Observe that negative x is the unique solution to x plus y is equal to 0. Negative x is the only thing that satisfies that. So if I take x and plus it with something and I get 0, then that other thing had to be negative x. So 2. Then, so I'm going to take -1 times x, and I'm going to add that with x, and I'm going to see if I get 0. if negative 1 times x plus x, if this ends up equaling 0, I need to show that does. If this ends up equaling 0, then this thing is negative x. It is a unique number such that when you add it with x, you get 0. We proved that there's one and only one number that has that property, namely negative x. So if this also has that property, if it has a property such that when you add it with x, you get 0, then this is in fact just another way of writing negative x. You with me on my logic there?
Yes.
So I got to prove that. Okay. How can we do that? Anyone have any ideas?
Wouldn't you do the same thing you just did?
No, this one's playing with ones rather than playing with zeros.
Could you factor out the x?
Factor out the x. Yes, almost. Let's multiply that by 1 really quick. But she has the right idea. I'm going to change the order I write this. I'm going to write this as x times negative 1. That's the same thing as negative 1 times x. Plus x times 1. Right? Didn't change anything. And now we can do exactly what Emma said. Coming down here and looking at this axiom. If I have x times something plus x times another thing, I can rewrite it as x outside times the sum of those two things. So that's what we mean by factor out. So this implies, or not implies, this is equal to, I'll just write the equals down here, I'm not sure if I'll have enough space there. Factor my x out, we get x, and we have negative 1 plus 1. When I factor the x out of there, using axiom 9 now. That's how we know that we can do that. Now, by definition, negative 1 is the additive inverse of 1. So by definition, negative 1 plus 1 is 0. So this is equal to x times 0. Then using theorem, whatever it was, theorem 6 or something like that, we know that any number times 0 is equal to 0. So what did I just really show? I showed that negative 1 times x, when you add it with x, gives you 0. Therefore, negative 1 times x is negative x. Remember, negative x is the one and only number. It's the one and only number I can add to x to get 0. That's the definition of negative x. I showed that it's also the case that negative 1 times x, when you add it with x, gives you 0. Since there's only one number that has that property, and I showed that this number has that property, then this number and that one number are the same thing. This is negative x. So therefore, negative 1 times x is equal to negative x. It is an additive inverse of x. There is only one additive inverse of x, therefore it is the additive inverse of x. Kind of a little bit weird there in the logic until you get it. And it feels like I'm saying the same thing 100 times. Good? Okay. The next one. Okay, this one's an interesting one. Well, you won't think so. It won't seem interesting until we get to the later one. But if we take the negative, just try it out here, prove that the negative of a product, the additive inverse of a product, is equal to the additive inverse of one of them times the other. So when you apply an additive inverse to a product, you only have to apply it to one of the terms. We'll find out that multiplicative inverse does not have that property. Additive inverse has it. Multiplicative inverse you have to apply to both. So negative x times y is the same thing as negative x times y. We're going to do this in the same way, I think. Not really sure how I'm going to do it yet. But what is negative x times y? I know that. Observe that negative x times y is the unique solution to x times y plus square equal to 0. Negative x times y is the only thing, the one and only number I can plug in there and get 0. So if I plug in another number there, namely that thing, and it also gives me 0, it had to be the same as this.
Okay.
So I know that negative xy is the one and only additive inverse of x times y. I'm going to show that this is also an additive inverse, and therefore it's really the same, since there's only one additive inverse. So they're equal. That's what I'm thinking I'm going to do here. We'll see if this leads us to a dead end. So then we have x times y, and I'm going to add to that negative x times y. Ideas? Besides Emma? What could we do to those terms? Something similar to what we did in the last one.
Move them to the other side of the equation. Could you multiply the left by one and make that?
It's not an equation. We're just rewriting this term. I want to show that this is equal to 0 somehow. I want to show this is equal to dot 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 0.
So multiply the left side, x times y by 1, and then factor out x times y. So you get 1 minus 1, which is 0.
Okay, I think you have the right idea. Let's just factor out the y though.
What about, okay.
We can just factor out the y, right?
Yeah.
So this is equal to y times, we have an x and we have a plus a negative x.
Oh, yeah.
You good?
Mm-hmm.
You're the same idea, just a little bit simpler, right?
Mm-hmm.
Okay. What is x plus negative x?
0.
0. That's the definition of negative x. It's the one and only thing such that when you add with x you get 0. So this is y times 0. We proved in a previous theorem that y times 0 is always equal to
0.
0. And so 3, therefore blah blah blah. Therefore, since negative x times y is an additive inverse of x times y, then negative x times y is negative x times y. You follow the logic there?
Yeah. Mm-hmm.
That's a unique number. This is the only number that satisfies that property. This number happens to satisfy that property. Therefore, this number is the same as that number. That's the overarching thinking there. Okay, next one. We're going to show that a negative times a negative is a positive. Well, not really, that's a special case of it. Show that negative x times negative y is the same thing as x times y. I want to show that negative x times negative y is equal to x times y. Let's see how we
Just
want to do that.
factor the negatives out and do the same thing you did in theorem 6.
So I can take one of them out. So I know that negative x times negative y, using our previous one, is equal to negative x negative y. And then I can rewrite using commutativity, change the order on those. But yeah, Adrian has the exact right idea. Times that. And then I can factor out that negative symbol using my previous proof as well, right?
Yeah,
Theorem 6.
Theorem
6.
Not 6, we'll jump to that one here in a second, but using this one first. This was if I had the negative times something, I can pull that negative out. So I can allow to pull that negative out. So this is equal to the negative of x times y. And now, using theorem 6, I know that negative negative is really just whatever that symbol is. So that's x times y. And we're done. Yeah, that wasn't so bad. Okay, next one. Prove that negative 1 times negative 1 is equal to 1. Well, that's just a special case of what we just did. So I don't know why I have that written as a separate thing. I don't even need to write anything. Negative 1 times negative 1 equals 1, that just falls from this theorem. Plug in 1 for x and 1 for y.
Yeah.
I guess you have to make the special case 1 times 1 is 1, but that's pretty trivial from our axiom, right? Axiom 7. So that was a bad one to put there. Maybe it's just one we use so much I decided it'd be useful to have it there. Okay, now we're ready for our definition of subtraction. So our definition of subtraction, I don't need to write it, you can just read here. Definition. What do we mean by x minus y? Our definition of that is x plus the additive inverse of y. So what do I mean when I say x minus 3? That's a shorthand way of saying x plus the additive inverse of 3. Remember, definitions are never necessary in mathematics. They just are shorthand ways of writing the same thing. It's just a convenient way of writing the exact same thing. That's what every definition is. They don't add anything new. They're just nice shorthands. So that's what we mean by subtraction now. So now we have a definition for subtraction. So let's prove our next thing here. Prove that negative x minus y is equal to negative x plus y. That one shouldn't be too bad with what we've proven. Someone want to try that one?
Is that skipping one?
Oh, did I skip one?
Theorem
Yeah.
11?
Oh, thank you. Theorem 11. So we have x times y minus z is equal to x times y minus x times z. Someone want to try it?
Sure.
All right. Feel free to erase and rewrite if you want, if you think you'll need more space, but I doubt you will.
Should be good. Do that x times y minus z is actually equal to x times y plus negative z by definition.
So just plugging in the definition of subtraction so far.
And then x times y plus negative z is equal to x times y, or sorry, x times y plus x times negative z by
Axiom 9,
axiom 9.
which is our distributive axiom.
And then x times y plus x times negative z is actually equal to x times y plus negative x times z, and it might help if I write it like this to be more
Pulling the
specific.
negative out, okay.
But that's by Theorem 8 here. Technically I would have had to switch the z over to here, but that's
Yeah,
just
so
gonna be
use
normal.
commutative property to switch the x into z, and then pull the negative z out.
Yeah, and that's the theorem.
Okay.
X times y plus negative x times z is actually equal to x times y minus x times z by our definition of
Yes.
minus. And yeah, that's all.
Wonderful. Anyone have any questions on anything she did there? All the steps make sense? Can you guys see in the back? I'll walk through it one more time in case you couldn't see it all. So we have x times y minus z is equal to x times y plus negative z. That's just using exactly what our definition is for subtraction. So then you have x times y plus negative z is equal to, she's just distributing the x across it. So x times y plus x times negative z, that's just using axiom 9. That's how you distribute. So then you have x times y plus x times negative z is equal to, the x times y she just leaves, plus, here we have x times negative z is the same thing as you can swap the order and write that negative z times x, and then you can pull the negative out, so you get negative x times z by Theorem 8. And so now going from x times y plus a negative number is equal to x times y minus that same number by definition of subtraction. Good. Let's see. We'll do one more, then we'll call it good. Leave the last couple as what we start with next time to remind us of all this, and then we'll jump into the book. So, proving this last one. So we don't need that. So, proof that negative x minus y is equal to negative x plus y.
How is that substantially different than theorem 8?
Then theorem 11 or theorem 8?
Oh, it's multiplication, sorry.
Okay. Yeah, this one almost falls for free. Let's see. We know that negative x minus y is equal to negative 1 times x minus y. How do I know that?
Theorem 7.
Theorem 7. Theorem 7 says negative 1 times a number is the same thing as negative that number.
Okay.
Good? Now, using what Emma just proved, when I have a number times a difference between two numbers, it's equal to that number times the first minus that number times the second. So now using what Emma just proved, this is equal to that number times the first, negative 1 times the first, minus that number times the second. Good? Which is equal to, once again, going back to theorem 7, negative 1 times x is the same thing as negative x. Negative 1 times y is negative y, so this is, we have minus negative y, which is equal to negative x plus negative y. That's what it means to subtract. When you subtract a number, that's the same thing as adding the additive inverse of that number. Subtracting some number is the same thing as adding the additive inverse of that number. And then we know from theorem 6 that negative y is the same thing as y. So this is equal to negative x plus y. And that's what we were after. Right?
Yes.
Yeah. Negative x plus y. Okay. So we'll call it there. We'll pick up with theorem 13 next time, finish out these last few, and then we'll be able to start the actual textbook.
Sorry.
Very welcome. And then for those of you doing the class for credit,